Okay, so far we've been talking a lot about overall rates and rate laws and experimental ways to measure that. So I guess in my kind of theoretical example, we know if A goes to, let's say, product B, this is what we're looking at, right? So we can measure product formation, we can measure the reactant consumption, so we have some overall rate law. But as you know from organic chemistry, mechanisms can be much more complicated. So, your starting material A might go to some intermediate B, which might go to maybe 2 equivalents of C, and then we go to the product D. So this would be 1, 2, 3 steps in our mechanism. So each of these intermediate steps, so these are called elementary steps. And they're what you propose in your mechanism. So the dogma of kinetics and mechanisms, reaction mechanisms, is that mechanisms can't be proven, only disproven. By which I mean, so you know A and D, and then you propose your mechanism in the meantime, because we don't actually know this. Or you might be able to state intermediate here and there. So you propose your mechanism, as you've done before on an organic chemistry exam. And so each mechanism is full of elementary steps. But unlike your overall rate law, overall reaction, each elementary step is going to have a rate law dependent on the stoichiometry. And the reason this is because we said that for the overall reaction, this overall stoichiometry doesn't tell us how it happens. So the rate law, your reaction rate, is dependent on kind of like the key transition states, right? Things coming together, or maybe one thing falling apart by itself. So that isn't given by our stoichiometry overall, but for each elementary step, that does tell us whether two things are coming together or whether one thing's falling apart. And that's why each elementary step has a reaction order corresponding to the stoichiometry of each step. So what I mean by that is, so let's say for the first step, well, we can call each step with their own rate constant, K1, K2, K3. So for the first step, let's say the consumption of A, so our rate is going to be negative dA dt. And then what I mean by it's dependent on our stoichiometry is because this is an elementary step, we can write that the rate of this consumption is going to be equal to K1 A, right? So yes, it's dependent on the concentration of A. So it's first order in A because we have one equivalent of A. So that's the first step. The second step would be, let's say, dB dt. So dB dt, or reactant B, has two elementary steps surrounding it. One for formation of B, and one for the consumption of B. And then as a result, the rate of the change of the concentration is going to be equal to formation of B, so K1A, this elementary step. And then the consumption will be, as we lose B, it will be minus K2B. So obviously we don't know what B is over time necessarily, unless you can look at it. It's an intermediate, so it's going to be small in concentration. But these are just the overall factors that govern how fast it's being formed or consumed. OK. And then let's see. So for the next step, third step, formation of 2C. So the rate is going to be 1 over 2 dC dt. And just like with before, it's going to be equal to K2 times B. Again, first order in B. And then here, 2C goes to D. It's going to be second order in C. So then, therefore, it'll have to be minus K3 squared. So that's the elementary step. And then lastly, for the formation of D, dD dt equals K3. OK. So like I was saying, experimentally, we have a hard time knowing the concentration of C and the concentration of B. So we might be able to measure D, we'll be able to measure A. So experimentally, this doesn't tell us all that much, but practically what you can do is, now you have the system of equations, you could in principle do maybe some more complicated data fitting software that can do it, or we can do some approximations that we'll talk about in the next video. But regardless, you have your proposed mechanism, so you can then somehow derive your ultimate rate law of ddt or negative dAdt. And then from there, if it's consistent with your proposed mechanism, then you can have a proposed mechanism that's good. If it's inconsistent, then you've just proven it. So that's kind of like the iterative step that you have to do. You propose a mechanism, calculate it out, see if it fits your actual data. If it doesn't, then you have the wrong mechanism. So that's kind of the overall way to do it. So elementary steps, again, the major takeaway is each elementary step, you can express the formation and consumption because we can do it by stoichiometry. Again, so what we can't say here is that the overall reaction, dt does not equal necessarily K times the concentration of A, right? Because that's overall not the intermediate steps that will involve will change our overall rate law. So that's kind of what's happening. Okay, let's see. One last example. Here, kind of one utility, which I think is kind of cool. So if we have a reaction of A going to B, and this goes at some rate K1, if it's reversible, B then can then go to A at a rate of K minus 1. So this is an equilibrium. Equilibrium reaction, there's a forward step and a backward step. So if this equilibrium is an elementary step, what we can say then is that dAdt is going to be equal to the consumption of A is negative K1 of A, and then the formation of A is going to be plus K minus 1 of B. So this is the overall expression. There's a forward reaction and a backward reaction. And then these are both elementary steps, if that's true. So this is our overall rate expression. And then, so at equilibrium, however, at equilibrium, this equals 0. So the formation and the consumption is going to be the same, so our concentration of A is overall the same. It doesn't change. And what this means is that if you then rearrange the terms, what we'll see is that K1 of A equals K minus 1 of B, and then therefore K1 over K minus 1 equals B over A. And then so this concentration of B over A is actually going to be our overall capital K equilibrium constant. So we've related for an equilibrium constant thermodynamics to the ratio of the forward and backwards reaction rate constants. So this is rate, lowercase k, with equilibrium, uppercase K. So we'll apply this later on. This will be very useful. But this is a kind of demonstration of how we can use elementary steps for, to find out more about our reactions.